All right, we are going to explore stretching and reflecting quadratic relations in this lesson. I'm going to start by directing you to the standard form of a quadratic relation. We were introduced to this in Unit 3. Today, we are only going to focus on this value right here. Now, on the note that I had posted online, I believe I had, and we're going to go right back to it right here. I believe I had 6 quadratic relations that I wanted you to create tables of values for. I'm going to focus on this one right here, y equals 4x squared, and I'm also going to focus on y equals 1/2 x squared. And again, if we go back to standard form, you'll notice there is no b and no c value, so you don't have to worry about those today. We are focusing on what happens when we play with the value of a. So if I bring you over here to my notepad, I've created 3 tables of values, okay? You'll notice in the X column, I'm using my usual suspects from grade 9, -2, -1, 0, 1, 2, and those will work today as well. And I am going to fill these in. So I know when I square -2, I get 4. When I square -1, I get 1, 0, 1, and 4. So that is my first table of values. Over here, I have to make sure I abide by the rules of BEDMAS. So the first thing I'm going to do, if I were to plug -2 into here, I would square it. -2 squared is 4. 4 times 4 is 16. -1 squared is 1. 1 times 4 is 4. 0 squared is 0. Anything times 0 is 0. 1 squared is 1. Times 4 is 4. 2 squared is 4 times 4 is 16, and we have one more table of values left to go. If I were to plug -2 in for x, -2 squared is 4, 1/2 of 4 is 2. If I were to plug -1 in for x, -1 squared is 1, 1/2 of 1 is 1/2. Anything times 0 is 0. If I were to plug 1 in for x, 1 squared is 1 times 1/2 gives me 1/2. And over here, if I would have plugged 2 in for x, 2 squared is 4 and 1/2 of 4 is 2. So you'll notice I have 3 tables of value here. What do they have in common? They all have the same x values or the same values of the independent variable, and yet they all have different y values with the exception of the fact that they all contain the ordered pair 0, 0. And now we're going to jump over to Desmos to see what this looks like. Okay, I am now in Desmos. I'm sure you used this in grade 9. If I were in class, I would be graphing all of these by hand. I just think this is a little bit more efficient for this virtual lesson here. So if we look at our first graph in red, I'm not sure how well you can see that, that is the graph of y equals x squared. And I like to call this our standard base parabola. Okay, there's nothing special about it. It opens up. It has its vertex on the origin 0, 0. Pretty standard shape, nothing too exciting here. Okay, and we did in fact create a table of values for this particular parabola. And so again, if we would have graphed it by hand, it would have looked something like this. Now let's go over here. And I actually want to look at the graph of y equals 2x squared. And you'll notice if we go back to our diagram on Desmos, our original graph was in red, y equals x squared is in red, and y equals 2x squared is in blue. And I want you to just kind of look to see what kind of impact that had. Okay, now I'll come back over here, and for my third graph in green, I'd like Desmos to graph y equals 4x squared. Okay, and hopefully at this point you see a pattern. So y equals 2x squared got more narrow than y equals x squared, and y equals 4x squared was even more narrow than the previous two. So just something to kind of explore here. Let me hide that. I should point out that we changed the value of a twice, and the vertex did not change. The shape of the parabola changed. Okay, let's come back over here and let's make this 1/2, which is 0.5. Okay, I'm going to hide these guys for a second. I don't really want to show them. So if I come back over here, I've got my original parabola, y equals x squared, and I have y equals 1/2 x squared, and you'll notice the parabola got more wide. Okay, now let's come back over and let's see what happens if I graph y equals 1/5 x squared, which is the same as 0.2. And if I come back to my graph, you'll notice it gets significantly more wide. Okay, and so again, if we were in class, I would be doing a number of examples. Hopefully you're starting to pick up on the pattern, but we will get there shortly. And let's come back over here. The last thing I want to show you, and we can reintroduce all of these graphs that we kind of hid. Here you'll notice all of these values of A have one thing in common, and they are all positive. Let's play around a little bit. Let's make the last value of A a negative number and see how that impacts the graph. And if we come back over here, okay, that's this guy right here. So I'm actually going to hide all these other graphs. And here, this is really nice because we can compare the graph of y equals x squared with the graph of y equals negative x squared. They are the same shape, they have the same vertex, it's just that one opens down and one opens up. Okay, so now I'm going to come back to the note that I would have posted for you on Edsby. And if you scroll down, I believe this is the 3rd page. At the bottom of the 3rd page, you have this number line, and I feel like this summarizes everything that we just talked about beautifully. So when we are looking at, again, I'll go back to my note, a quadratic relation, the A value serves quite an important purpose. It helps us to determine the direction of the opening of the parabola as well as the shape of the parabola. So if I come back over here, okay, 0 being sort of my benchmark, if the A value is positive, as that shows here on the number line, that means the parabola is going to open up, whereas, I think I need to scroll over here, if the A value is negative, the parabola opens down. And we knew that already, but now we're going to express it with some sophisticated language. We are going to say there has been a reflection in the x-axis, which is exactly what we saw, which is exactly what we saw on Desmos, okay? When the A value, we can get rid of all these guys because we're done looking at them. 1, 2, 3, 4. Okay, when we compare the graphs of y equals x squared and y equals negative x squared, one opens up, one opens down. We would say that this guy has been reflected in the x-axis. So that's the first thing we look for when we're examining the value of A. Let's go back to the note. Okay. Now we're going to focus on the shape of the parabola. We did some sort of experiments there, and we noticed that when we played around with the A value, the parabola either got more wide or more narrow. And I find this graphic organizer really summarizes it nicely. So the further we move away from 0, the more narrow the parabola will get. And that is why, and I'll go back to Desmos here, that is why y equals, see if I can get the whole screen in here, y equals x squared is not as narrow as y equals 2x squared. And the most narrow of those three would be y equals 4x squared. Let's go back to my note. So the further we move away from 0, the more narrow the parabola gets, and we call that a vertical stretch. So you could have a vertical stretch on its own, or we could come over here, we could have a vertical stretch for a parabola that was already reflected in the x-axis, and I'll talk more about that later. Now, the opposite of a vertical stretch is a vertical compression. A vertical compression exists when the value of A lies somewhere in here, okay? So anywhere between -1 and +1. So for example, 8/9, 1/2, 1/5, 2/3. All of those A values would result in a vertical compression, which makes the parabola more wide. Okay, so let's finish up by sort of putting everything we just talked about together. These are all quadratic relations. Each of them have a vertex of 0, 0. Okay, so these are all just plain Nothing special. They haven't been moved. They're sitting right there with their vertex on the origin. If we look at number 1, if I was asked to describe the transformations, I would say that number 1 has undergone a reflection in the x-axis. And again, I know that because of that negative number. The a value is -1. The negative tells me there was a reflection in the x-axis. The fact that the coefficient is 1 means that it was not stretched or compressed. Okay, for number 2, I would say that there has been a reflection in the x-axis and a vertical stretch by a factor of 2. That made the parabola more narrow. Number 3, there is no negative, so there was no reflection in the x-axis. I would say there's a vertical compression by a factor of 1/3, which made the parabola more wide. Number 4, reflection in the x-axis, vertical compression by a factor of 4/5. Number 6, no reflection in the x-axis, vertical stretch by a factor of 6. Again, it's a vertical stretch because 6 does not lie in between -1 and 1. And then finally, example 6, there is no reflection here, but I would say that there's a vertical compression by a factor of 1/2. This is something I like to do in class sometimes. Once we've looked at a whole bunch of examples, I'll ask you to rank them from most to least narrow. So remember, the further you get away from 0, the more narrow the parabola gets, okay? 6 is the furthest from 0, so I would say that this guy is the most narrow. Make sure you guys can see that. There we go, most narrow, rank that a number 1. Now, looking at just the numbers, we're not concerned whether or not it's been reflected or not. I believe 2 would come next. Okay. This guy would be next because he's got an invisible 1 right there. Again, the closer you get to 0, the more wide the parabola gets. So I believe this guy would come next because that converted to a decimal is 0.8. Okie dokie. And then I believe this guy would come. And then the closest to 0 here would be the 1/3. So he would be the least narrow, or in other words, the most wide. Now, if I wanted to just kind of go through and again review some things we've talked about before, this guy opens down, this guy opens down, this guy opens up. And again, that's dependent on whether or not there has been a reflection. This guy opens down, he was reflected, the a value is negative. This guy opens up, and this guy opens up. Okay, what do these all have in common? They all have a vertex on 0, 0. Some open down, some open up, and they are all different shapes. When two parabolas are the exact same shape, we say that they are congruent. And we can tell if they have the same a value. So down here, okay, let's say I looked at the parabola y equals 4/5x squared, okay? This guy and this guy would be congruent. They are the same shape. I understand that this one was reflected and this one was not, but that doesn't matter. They are still the same shape because they have the same vertical compression factor, the same value of a. I'd like to conclude this lesson just by examining this example here. When we talk about the value of a and how it impacts the ordered pairs on the parabola, okay, as you noticed on the very first exercise we did together, let me pull that back up right here, okay, we had 3 different quadratic relations with 3 different a values. This guy has an a value of 1, this guy has an a value of 4, and this guy had an a value of 1/2. You'll notice that when we changed the a value, the x coordinates of the quadratic relation did not change. The y coordinates changed. How did they change? We'll have a look. Here is the standard quadratic relation, right? Nothing fancy, no number in front of x squared, so the a has an invisible 1 value right there, okay? Then, when the a value was 4, I essentially just took my y values from here and multiplied them by 4, okay? When the a value was 1/2, I essentially took my y values over here and multiplied them by 1/2, okay? So what can we take from that? If you go back to your note, when there is a reflection, a vertical stretch or a vertical compression, the x coordinates of the ordered pairs are not impacted. The only thing that changes is the y value, and it changes by being multiplied by the a value. So if we look at this example here, let's say that was an ordered pair on the parabola, and the a value was -2. So let's talk about what that means. If the a value was -2, that means that the parabola was reflected in the x-axis and vertically stretched by a factor of 2. So what they're saying here is this was an original ordered pair, then we did those things to the parabola. What is the new ordered pair? The x value goes unchanged, and all I did to the y value was multiply it by the a value. Same thing with the next example. You have an original ordered pair of -2, -20. The a value is 1/10, which means there was a vertical compression by a factor of 1/10. What is the new ordered pair? The x value didn't change, but the y value, which initially was -20, was multiplied by 1/10, resulting in a y value of -2. And I just want to note that you are not responsible for example number 6. Okay, thank you.